So today we've got another type of Lie algebra to talk about, and it is the reductive Lie algebra. It's defined that a Lie algebra is reductive if its adjoint representation is semi-simple. And of course comes with a proposition. It says a Lie algebra G with radical R has the following are equivalent. I kind of worded it weird, but it's just like we're setting up the Lie algebra G and radical R, and so the following are equivalent. G is reductive. Our second equivalent is that the derived algebra of G is semi-simple. I guess I'll put in brackets as always that G reductive is that its adjoint is semi-simple, even though that's already above. It's just easier to compare with like things like this. C is that G is the product of a semi-simple algebra and a commutative algebra. D. G has a finite dimensional representation such that it's associated by linear form, its version of the Killing form. Is non-degenerate. Condition E, there's lots of equivalent definitions for this, it looks like. Condition E is that G has a faithful, semi-simple, finite dimensional representation. F is that the nilpotent radical of G is 0. Condition G, our last one, finally, we've got 7 here, is that the radical of G is equal to its center. And we've got to show these are all equivalent. So A implies B. We have G, the adjoint of G is semi-simple, we want that its derived algebra is. So given the adjoint of G being semi-simple. We have G as a direct product sum, actually they have it. I don't know if there's a difference, but in this context it's the direct sum of minimal, non-zero ideals AI and hence we have G is isomorphic to the product of AI. With each AI having no non-trivial ideals and so is either simple or is one-dimensional and commutative. Thus, keep in mind we're trying to show that the direct algebra of G is semi-simple. Thus, dg is the product of these AI for the AI which are simple and so is semi-simple. Alright, now we're going to assume that G is the derived algebra of G is semi-simple, and we want to show that G is the product of a semi-simple algebra and a commutative algebra. So we're given dg is semi-simple. Then we know that G is isomorphic to the product of dg with some h. So h is equal, that's by a previous corollary, which means h is isomorphic to g over dg, which makes it commutative. Alright, now we're given that C is the product of a semi-simple and a commutative algebra, and we want that it has a finite dimensional representation with a non-degenerate bilinear form. So we're going to let G1, G2 be Lie algebras with rho I a representation of Gi with an associated bilinear form beta I. Rho 1 and rho 2 can then be considered representations of the direct product of G1 and G2, I'm guessing with having the other algebra just sent to 0. And then we let rho be their direct sum. clearly the bilinear form on G by P is the direct sum of the bilinear forms we have there, and hence inherits their non-degeneracy. Thus, we can cover C to D in two cases. First case is where G is semi-simple. Then the adjoint representation admits its bilinear form, which is the killing form. Which we know is going to be non-degenerate on a semi-simple algebra. And the second case is when G is equal to our base field K, then the identity representation is going to admit a non-degenerate bilinear form. Now, next up is, of course, D going from D to E, which states if that G has a finite dimensional representation with a non-degenerate bilinear form, then it has a faithful semi-simple finite dimensional representation. So we're going to let rho be a finite dimensional representation of G with bilinear form beta. Then, by previous proposition, there exists a finite dimensional semi-simple representation rho of G such that letting n, which is the kernel of phi, is orthogonal to G with respect to the bilinear form beta. The beta is non-degenerate. Then n is just the zero element, so sigma is faithful. Now E implies F. says that if G has a faithful semisimple finite-dimensional representation, then the nilpotent radical of G is 0, which is true. F implies G. If the nilpotent radical of G is 0, then the radical of G is its center. How did I introduce these? Given is the word I'm using. Given the nilpotent radical of G is 0, we have at the intersection of the derived series of G and the radical of G is 0 by a previous proposition. And as the bracket of G and R must lie within the intersection of DG and R is just going to be the center. And finally, we have to go full circle to get full equivalency to show that G implies A. Just stating that if the center of G is its radical, then it is reductive, so that its adjoint representation is semisimple. Given that the center of G is equal to R, the adjoint representation of G is identified with a representation of G divided by R, which is itself going to be semisimple. So the representation is likewise semisimple. And we are done. That's equivalence of all these. Alright. Now we have a remark. If a Lie algebra G can be written as the product of a commutative algebra and a semisimple algebra, they're commutative and semisimple respectively. This decomposition is unique. We see that the center of G is equal to the center of A times the center of B, and so is just all of A. And the derived series of G is the derived algebra of A times the derived algebra of B, which is just all of B. Alright, brings us to a corollary. And this one comes in 3 parts. This is, the first part is the finite product of reductive algebras is reductive. B is that if G is a reductive Lie algebra of center C, every ideal of G is a direct factor. We have that every ideal is the product of its intersections with C and DG. And is reductive. And C, our third and final part of the corollary, is that every quotient of a reductive algebra is itself reductive. Let's get to the proof here. So we have from our previous result where the product, where reductive is the product of a semi-simple and commutative algebra, our previous result. Now, suppose G is reductive. Let A be an ideal of G. Since the adjoint representation of G is semi-simple, A has a supplementary ideal B and G is identified with A times B. For all x in G, let rho of x be the G adjoint of X restricted down to A. And then rho is a semi-simple representation of G which is 0 on B and defines by quotient the adjoint representation on A. Hence A is reductive. And so are B isomorphic to G over A. Now we're going to let D and D prime be the centers of A and B. Then A is the product of D and the direct algebra of A. B is the product of D prime and the direct algebra of B. The product of D and D prime is going to be the center. The product of the direct algebras of A and B is going to be the direct algebra of G. So that gives us that A is equal to the intersection of A and C plus the intersection of A and the derived algebra of G. And that's everything. Now we've got 2 more steps for today. The first is another proposition. Same setup as always. G is going to be a Lie algebra with radical R and nilpotent radical S. First part of our proposition is that S is equal to the bracket of G and R, which is equal to the intersection of the derived algebra of G with R. B, our second condition is that S is the intersection of the orthogonals of G with respect to the bilinear forms associated with the finite dimensional representations of G. Let's look at the proof. So, just based on what we know, we see that the bracket of G with its radical is inside the intersection of its derived algebra with its radical. Now, we also have that the intersection of the derived algebra of G and R is equal to S by a previous theorem. So we're going to let G be equal, G prime be G over the bracket of G and R with F from G to G prime the canonical homomorphism. And then the image of the radical under F is the radical of its codomain, which means we can send this equation under F to get that G prime bracket R prime is 0, and so that R prime is the center of G prime. So we saw that G prime has a finite dimensional semi-simple representation, so that S has to be inside the bracket of G and R. That's it for part A, because we have like a circle of inclusions. Yeah. Part B, we're going to let T be the intersection of orthogonal of, I guess, the orthogonals as described in B. So we're setting T to be equal to the intersection of the orthogonals of G with respect to the bilinear forms associated with the finite dimensional representations of G, and we want to show that that T is then equal to S. We have that S is inside of T from our previous result. We also have, though, that G over S has a finite dimensional faithful semi-simple representation, so it has a finite dimensional representation rho such that the associated bilinear form is non-degenerate. Considered as a representation of G, rho has a associated bilinear form beta on G and the orthogonal of G with respect to beta is S. So T has to be included inside of S. And we're done. It's worth noting, even if S is non-zero, we may have non-degenerate symmetric bilinear forms on G. Not being associated with any representation. So this only covers the non-degeneracy of symmetric bilinear forms generated by representations, as you can tell. And we have a corollary at the end. We're a little under time, not exactly where I want to be, so I might go a little slower on this, but it's not a whole lot. Corollary. How long is the next chapter, actually? Too long to do, I think. So, corollary. We're going to let G and G prime be Lie algebras. S, or alternatively S prime, be the nilpotent radical of G, or alternatively G prime, and we're going to let a function f from G to G prime is going to be a homomorphism. Now there's two conditions here. A is that the nilpotent radical of G prime is I think actually it says f G onto G prime, so I think this is going to be surjective once again. And get the nilpotent radical of G prime is going to be the image of the nilpotent radical of G under F and B, we're going to have that G prime is reductive if and only if S, the nilpotent radical of G, is contained within the kernel of our F. We have that B implies A immediately, so we only actually need to show A. So proof, we're going to let R and R prime be the radicals of G and G prime. Then we have that long equation, so I'm stalling for a new line. The nilpotent radical of G prime is the bracket of G prime with its radical, which is equal to the image under F of G and the image under F of its radical, which is F is a homomorphism, so we can bring that to the front of the bracket, which is then definitionally S. And we are done. Yeah, if I was braver, I would go for another chapter, but I think I will call it here. And then we'll do, because we did like, that's a bit over 2 pages. That's another like page and a bit, so that's going to be another 20 minutes or so. That's, I'm really debating whether or not to go for it, but I think I'm gonna call it here. Because yeah, tomorrow we can go, next video we can go through 2 chapters pretty easily, I think. So yeah, we'll call it here. Thanks for watching.